is 0. Okay, that's the definition of what it means to be conservative. If I take any closed curve, the work will always be 0. The contrary, not conservative means somewhere there is a curve along which the work is not 0. If you find a curve where the work is 0, that's not enough to say it's conservative. You have to show that no matter what curve I give you, if it's a closed curve, it will always be 0. So what that means concretely is, if you have a force field that's conservative, then you cannot build somehow some, perpetual motion out of it. You can't build something that will just keep going, just powered by that force, because that force is actually not providing any energy. After you've gone, one loop around, nothing's happened from the point of view of the energy provided by that force. There's no work coming from the force. While if you have a force field that's not conservative, then you can try to actually maybe find a loop where the work will be positive, and then, that thing will just keep running. So actually, if you look at magnetic fields and transformers or power adapters and things like that, you extract energy from a magnetic field. Of course, you actually have to take some power supply to maintain the magnetic field. So a magnetic field, you could actually try to get energy from it almost for free. A gravitational field or an electric field, you can't. Okay, so, and now why does that hold? Well, if I have a gradient field, then if I try to compute this line integral, I know that it will be the value of a function at the end point minus the value at the starting point. But they're the same, so the value is the same. So if I have a gradient field and I do the line integral, then I will get f at the end point minus f at the starting point. But they're the same point, so that's 0. Okay. So just to reinforce my warning that not every field is a gradient field, let's look again at, our favorite vector field from yesterday. So our favorite vector field yesterday was negative y and x. It's a vector field that just rotates around the origin counterclockwise. Okay? Well, we said if you take, say you take just the unit circle, for example, counterclockwise. Well, remember we said yesterday that the line integral of f dot dr, or maybe I should say f dot tds now, so because the vector field is tangent to the circle, so on the unit circle, f is tangent to the curve, and so f dot t is length f times, well, length t, but t is a unit vector, so it's length f, and the length of f on the unit circle was just 1. So that's the integral of 1 ds, so that's just the length of a circle, that's 2 pi. And 2 pi is definitely not 0. So this vector field is not conservative. And so now we know, actually, it's not the gradient of anything. Because if it were a gradient, then it would be conservative, and it's not. So tells you, it's an example of a vector field that is not conservative. It's not path independent either, by the way, because, see, if I go from here to here along the upper half circle or along the lower half circle, in one case I will get pi, in the other case I will get negative pi. I don't get the same answer. And so on and so on. It just, fails to have all of these properties. So maybe I will write that down. It's not conservative. Not path independent. It's not a gradient. It doesn't have any of these properties. Okay, any questions? Yes? How do you determine whether something is a gradient or not? Well, that's what we will see on Tuesday. Yes?
Is it possible that it's conservative but not path independent?
Is it possible that it's conservative and not path independent, or vice versa? The answer is no. These two properties are equivalent, and we're going to see that right now. At least, that's the plan. Okay. Yes?
So if it's not conservative, then it's impossible to draw level curves that are perpendicular to it at every point?
Let's see. So you said if it's not path independent, then we cannot draw level curves that are perpendicular to it at every point. I wouldn't necessarily go that far. You might be able to draw curves that are perpendicular to it, but they won't be the level curves of a function for which this is the gradient. I mean, you might still have, if you take this gradient field and, scale it, but in strange ways, multiply it by 2 in some places, by 1 in other places, by 5 in some other places, you will get something that won't be conservative anymore. And it will still be perpendicular to the curves. So it's more subtle than that. But certainly, if it's not conservative, then it's not a gradient, and you cannot do what we said. And how to decide whether it is or not, that will be Tuesday's topic. So for now, I just want to figure out again, actually, let's now state all these properties. Oh. Actually, let me first do 1 minute of physics. So let me just tell you again, what's the physics in here. So if a force field is the gradient of a potential so I'll still keep my plus sign. So maybe I should say this is minus physics. But